a determination of the skidding car lab. And so what you have to first know is something called the work energy theorem. So it's the skidding car lab. And so we're going to have somebody speed down Carroll, and at the intersection of Carroll and Brook and Breck, we're going to slam on our brakes. And using this work energy theorem, well, shoot, I forgot the word energy. Sorry about that. So work energy theorem, we're going to determine how fast was the car going. So this car, so like you're going to speed down Brook and Breck, not Brook and Breck, but Carroll rather, and then when you get to Brook and Breck, we're going to be standing there, you're going to slam on your brakes, and we're going to measure your skid mark. So let's first of all talk about what type of energy lake does your car have before you ever stop? Kinetic energy, very good. So you're going to have kinetic energy at the beginning, and what the work energy theorem says is the work of the kinetic energy must end up equaling the what? The work, very good. So what is actually stopping your car? Friction. So this is going to be the work done by friction here. So I'm going to put a little F there. I might as well put down friction down here. Right? Well, I don't know either one of those two things, so now we got to substitute in formulas for them. So Lila, what's the formula for kinetic energy? Very good. 1/2 mv squared. Great job. So you got kids eat 1/2 of most of their vegetables in a square meal. And what was the formula that we just wrote down for work during the other lab, Emma? That's perfect. That's right. F times D. Now, we're not going to put the cosine of theta because the force and the distance are going in the same direction. So what is that going to be the distance of, Megan? That's right, the skid mark. Perfect. So what we're going to do now, though, is we have to figure out what this force of friction is. So you got to remember from last chapter what the formula for friction was. And if you remember, we had this little triangle, and we drugged those wooden blocks across the sandpaper and the rubber and all that, and we used this formula right here, that mu is equal to the friction force over the normal force. Or you could say that friction is fun. Remember that one? So since I don't know friction force, what formula can I put in for it? That's right, mu times Fn. So over here for the friction force, I'm going to substitute that in. So we're going to write down everything again. 1/2 mv squared equals, but I'm going to put in that mu times Fn, and then bring down my distance to the skid mark. Now what we have to do is look up what mu is. On your paper on the lab there, what does it say that mu is between rubber and asphalt? 0.8. So we know that mu is going to equal 0.8. But now I got to figure out what the normal force is. Does anybody remember from last chapter what the normal force is the same as? The weight. Very good. So if normal force equals weight, and weight equals what formula? And weight equals what formula? Mass times gravity. I can now substitute in mass times gravity in for the normal force here. Okay? Okay, so what we're going to do now is we're going to fill in that normal force, and I'm going to bring everything down. 1/2 mv squared equals mu, but for Fn, I'm going to put in this mg over here, and this is once again the distance of the skid mark. Well, guys, since you have a mass on both sides, what does that tell you? They cancel out. So that tells you right there that a smart car and a semi-truck will skid the same distance if they're going the same speed. It makes no difference how heavy you are, you will skid the same distance. Now, the whole point of the lab is to discover what? That's right, the velocity. So I got to get this velocity by itself. So what do you got to do to both sides, Laura? I'm going to divide by 0.5. Well, dividing by 0.5 is the same thing as multiplying by 2. So I'm going to multiply this side by 2, and I'm going to multiply this side by 2. And so that means that gives you v squared equals 2 times mu GD. Now, what do you got to do to get the square? I'm sorry, to get rid of the square, you got to do what? Square root both sides. So I'm going to square root this side, square root this side, And so my answer ends up being that velocity is equal to, now to make this easy to remember, I'm going to switch these letters around. So it spells to Doug. Now you could also go the other way and make it too good, but not a lot of people spell good with this U. So anyway, so I just remember the square root of 2 Doug. So guys, let's for those of you that are not here that still are going to have your lab due because you took the extra vacation day, I'm going to say now, guys, we're going to get our data outside, but this is for the people that weren't here. Your skid mark's going to be 26 meters long, and we're going to say that you were going 50 miles per hour. Well, that's the first thing I got to get you to remember is how to do those conversions. So let's say that I want to convert let's say I'm going to convert 30 meters per second to miles per hour. Now, at the top of your lab there, it tells you what all the different things mean. So I got to get meters to miles. How in the heck are we going to do it? I got to get meters to cancel out, so where are they going to go? On the bottom. I know how to get from meters to kilometers. Very good. So I'm going to put a 1 next to the prefix unit. How many meters are in a kilometer? 1,000. Okay. So now my meters have canceled out. Okay. Now I got to get kilometers to cancel out. So Brenda, where are you going to put it to cancel it out? On the bottom. Very good. Trying to get from kilometers to miles. How many miles are in a kilometer? How many kilometers in a mile? 1.6 what? 1 and then 1 mile. And here I'm going to go from seconds to hours. But seconds over here is on the bottom. So where do you got to put it to cancel out? And there's 3,600 seconds in 1 hour. And so now what we're going to do is multiply all that out. So one last thing here. Let's just say your answer for this formula up here comes up to 30 meters per second. You're going to convert that to miles per hour, and then Lake is going to let us know how fast he was going when he actually slammed on his brakes. Okay? And we're just going to compare those two numbers together. Hopefully we're going to get that. Now, I'm going to tell you this. When you get your answer, this will be the minimum speed that that car was going. It could have been going faster, and the brakes just didn't grab fast enough. Make sense? So whatever answer you get is the absolute minimum speed that that car was going. All right, that's your lab. Hope you have a great day. Love you.